So hi guys, thank you for coming this afternoon. Pablo Fraile, I'm Director of Developer Ecosystems at ARM, and have with me Kristoffer Benjaminsson, CTO of Fast Travel Games. So I'm gonna grab this and hope that I can use it. So we're going to talk about how we managed to create some console experiences on mobile using Apex Construct, which is Fast Travel Games' latest title. So I just wanted to give you some context of why we are here. I just want to give you a quick quick chat about ARM. So we are, you may know ARM as the company who makes processor for mobile devices. We are pretty much, if you have a mobile phone in your pocket, chances are the processor inside is powered by ARM. We are also quite big on mobile GPUs. So our ARM Mali GPU is about 50% of the mobile market, and last year we shipped about 1.2 billion GPUs. So obviously gaming is quite an important part of what we do, and when we were looking at gaming experiences, we were about this time last year we were thinking, so what would it take to bring a console-like experience to mobile? What would it be? What would it take? What would it be involved? So around that time, we were talking to Kristoffer, and we found that they had the same vision. So we decided to work together and did a quick project that we're going to talk about.
Thank you, Pablo. So Fast Travel Games is a VR game studio in Stockholm, Sweden, and Apex Construct, the topic of this presentation, is our first title. Before we jump into and show and talk about how we got it to run on mobile VR, let's have a quick look at the game.
I really hope you're ready for this.
Okay, so Apex Construct is a game that is built for VR from the ground up. And what we mean with that is that we require motion controllers and positional tracking for your head for the game to be played. You use your hands when interacting with the environment, and you also use your hands when using the bow and arrow, our combat mechanics. We mix high-paced action with slower-paced slower-paced exploration and puzzle solving. And it's being launched on PS4 and PC. So why are we at Fast Travel Games interested in mobile VR? The answer lies in our technical vision, in that we want our players to be able to play immersive experiences wherever they are, whenever they want, and not be bound to a specific location. What's really interesting with mobile VR is that it has the potential to offer the same experience that you have on PC and console. There's obviously a lot of ways to accomplish this, but we believe that low-power CPUs and GPUs are the best option right now. And the thing that we're kind of waiting for is positional tracking for heads and hands. So, is Apex Construct on mobile even feasible? It is, after all, a title built for PC and console, and we require motion controllers and positional tracking. But if you look at the performance range that you have in the game, going from a base PS4 up to a high-end PC, that range is already quite broad, and we had already built a lot of tech and technologies to handle that range and scale between the different platforms. So we felt that adding mobile to the mix should definitely be doable. And also, mobile CPUs and GPUs are really quite powerful, so the gap might not be as big as one might think. So for us, this project was a first reality check. We had the game, it was done, it was running. What would it take to get it to run on mobile VR? What kind of sacrifices would we have to make? Would we be comfortable with doing those sacrifices? What bottlenecks would we run into? Would it be similar to what we saw when optimizing for console? Lots of questions. But all through this, we had this working theory that even if the actual fidelity when comparing screenshots side by side would be different, it would be lower on mobile, the perceived fidelity inside the headset would be similar. And that is really all that matters. As I said, we've built a bunch of tools and technologies to help scaling the game. So I'm going to mention a few of those. First up is sublevels. You can think of sublevels as layers in Photoshop. It allows us to divide a level into separate files, so different people can work on the same level at the same time. We then have an automated build process that merges these parts together depending on which quality target that we are going for. So this allows us to have much more detail on higher end platforms, for instance, than we do on lower end. Next up is bucket streaming, and it's not really a streaming system in the way that we load and unload data at runtime. It's more a way for us to control exactly which assets that are active at any point in time. So as the player plays through the world, we enable and disable different things. And the theory here was that we could save a lot of performance by making sure that the engine only had to consider as few assets as possible. And this was really a big help to us. Next up is quality set selectors. It works on the same premise as bucket streaming, but on a single asset. So it allows us to control parts of an object that should be enabled or not, depending on the quality target. So if you take an effect as an example, we generally have much more particle systems running on PC than we do on mobile. In Apex, we use a modular mesh set to create our environments. It's an awesome and great flexible way to author content, but it comes with a cost with a lot of draw calls, unless you can batch them efficiently. And again, instead of relying on the engine to do that for us, we created tools that gave the power to our artists that they could use their domain and context knowledge and make the decisions of which object that should be combined and batched together. And this allowed us to reduce draw calls a lot. I'm not going to go into physics. Let's just say that you can save a lot of precious CPU time by making sure you have sane colliders for your objects.
Right. So when we got involved with this project, we had to do a fair amount of content optimization on mobile. And in ARM, we have a number of tools that we use for this purpose. We call it Mali GPU tool suite that includes an offline compiler that allows you to compile your shaders and predict performance. We have a Mali graphics debugger, which is a debugger and profiler for GPU calls on your GPU API calls. Then we have Streamline, which is a GPU CPU profiler that lets you see hardware counters on a timeline. So when we looked at this problem, first of all, what you try to do is to profile the content to understand where is the issue, which assets are giving you problems, which frames are the heaviest. And then so as you profile the content, you understand where the issues are, then you decide how you're going to optimize it. And optimization can be quite a creative process because basically you can do pretty much anything you want. In this particular case, we were trying to optimize the content in a way that didn't affect the visual experience. So everything we did was trying to remove load on the hardware that was not contributing to the visuals on the game. So on one hand, we did mesh simplifications, taking the mesh load from about 2.4 million triangles to 1.4 million triangles. So that's about 40% down, and that reduced our vertex load significantly. The shaders, the default shaders on the game were standard surface shaders with baked lighting, so that was quite heavy for mobile again. So we replaced that with optimized versions that, as you can see, pretty much didn't impact the visual fidelity. And then draw calls is a really significant issue on mobile, particularly in high fidelity mobile gaming like this. So to reduce the number of draw calls, we looked at occlusion culling, so removing rendered objects that were not actually being displayed on the screen because they are occluded, and merge some meshes to reduce the number of draw calls even further. So the other aspect of the project was optimizing the content on one hand, but then actually how could we replicate the gameplay experience on a mobile device with the constraints we have on a Gear VR headset. So one of the key issues we had is obviously Gear VR doesn't have tracking, head tracking. So we implemented our own version of head tracking using AR Core and the Samsung phone sensors. We did the project integrating all of that into the engine, and we have the resources at the end of the call. If you talk, if you want to have a look at it, it's all on our website how we did it on the source code, and it's quite neat. And the result is like this. This is Daniele, one of our developers, using the head control just on a Gear VR, using the front or the rear-facing camera on the phone, and it works quite well for the demo. It's probably not. You could do better with dedicated hardware, and obviously we're getting there, but it did the job. So this is what it looks like in the end. On the left-hand side, you have PlayStation VR. On the right-hand side, you have Gear VR. Our own version of the game, and you can see the visuals, the assets, the whole scene is identical. The gameplay is also very similar. So there are not. I think the differences are very small. The only difference is when you come to this point where you have to actually shoot, because we only had one controller in Gear VR. We couldn't do the bow and arrow effect, so we had to shoot the evil robots instead of sort of throwing arrows at them. But apart from that, I think we were very pleased. What's coming up in the future to help us get even closer to where we really want to be? Vulkan is a low-level API. If you're not familiar with it, is going to over time replace OpenGLES as a mobile API for particularly on Android, and it has a number of advantages over GLES. It improves the efficiency of the CPU by making better use of multi-threading on mobile devices. It improves the number of the use of draw calls. There are things like multi-view, particularly important on mobile VR, that helps reduce the draw call count even further. Coming up in version 1.1, and there are other bits and pieces on things like foveated rendering and so on. So in conclusion, from our point of view, I think the experience has been really positive. We got very close to what we wanted. I think looking into the future, things like Vulkan and obviously better hardware, more powerful hardware, and all-in-one headsets, including dedicated hardware for things like inside-out tracking and controllers and so on, are going to make a huge difference.
I mean, from our perspective, again, coming back to the point about the perceived fidelity, this project really showed that you can really reduce a lot of stuff, and you can really create as immersive experiences on mobile that you can on PC and console. You just need to know your target hardware and how to massage it the right way, so to speak, and really pay attention to performance all along the way, and then you can create some really cool stuff. So a lot of these learnings are obviously going into our future titles.
And if you want to know more, here are some resources online. There are some of the project, the work we did, the tools we've used, and so on. It's all available online. So go have a look at it. That's it.
Questions? Yes.
Wow, he's eager. Like I was going to say, you have time for questions, but you're eager. No problem. Here, you have it.
Hi, thanks for the talk. Is, in your experience, the mobile tracking using the phone camera good enough for accurate head tracking? Or are there any problems regarding, for example, lighting or some other environmental factors?
I would say that, as Pablo said, it was a great experiment, but it's not on the same quality level that you have with a dedicated hardware. So, the Rift Vive is obviously much better than
Yeah. I think what we were trying to do is to prove the point that it can be done, and one of the reasons we tried to do it that way is because if you think about AR Core and all of the the APIs and the vision system is adding load to the hardware, so it has to manage all of the gameplay, all the visuals, plus on top of that the input from a high resolution camera to do a job like that. So it was interesting for us whether we would be able to fit it and do the whole gameplay at the same time, and we could.
And a follow-up, are you aware of third-party positional tracking hardware such as anti-latency, which is a sensor that you can attach to Gear VR?
Yes.
Have you been developing with it?
We haven't yet. I mean, from Fast Have Games perspective, we are kind of waiting for the stuff that comes out of the box. And that's what we are targeting primarily. But who knows? I mean, it's, after doing this, it's definitely a possible option. Yes.
All right, thanks.
Okay. More questions? Maybe I put myself here so I can see if there are. I do have a question while they think about it. On market-wise, because you were used to work with PC and console, and you had worked with VR before, but now mobile, I understand. What do you think is going to be the impact business-wise on the market with the new release?
I mean, this wasn't a release of the game. This was just a experiment to see if it was possible to do. But if you ask me what I think about mobile VR, then I think it's definitely going to be, the type of hardware or the type of VR that's going to hit mass market the quickest. It has the potential of being cheapest, but also being more accessible. So I'm a strong believer in mobile VR.
Sorry, I missed that. I actually thought you were. Now I wanted to play it.
I'm afraid you can't. It was just a demo we've shown in a few places. We showed this demo at GDC and a few other events, but it's not published and it won't be published.
Did you guys test it with public to get feedback? Do you have feedback about the project?
Yeah. So the feedback we got in those events is very positive. I think people. Particularly liked, as Kristoffer says, the mobile aspect of being completely untethered, so you can move around. You don't have to necessarily look to in the case of a PSVR, you don't have to look at the screen, so you can move face backwards. So it gives you all the freedom that you don't have on a tethered device, and I think that's really, really important. You can't underestimate how much of a difference that makes.
Any other questions? Yes. A second. Let's go ahead.
Hi, and thanks for the talk. How did you code the Unity sub-level system? Because it was in one scene, right? And how was the sub-level thing?
Well, it's basically built around additive scenes. So we have our own framework, kind of loading and unloading things.